Dear learners, welcome to lecture 3, week 1. So, in lecture 2, we have done the basic definitions of cell geometry and we have derived the first fundamental form of surfaces. So, from that starting point of, I will just quickly review that how to derive a first fundamental form of surfaces. Let us say alpha and beta, they are two curvilinear coordinates and that will assume a surface and divided into the grids. Basically, these lines are parallel to alpha coordinates and beta coordinates. And from a reference coordinate system O, where x1, x2 and x3 will get a, let us say, point M and the position vector. So, the position vector R can be written as x1, which is a function of alpha and beta, E1 hat, which is a unit vector along one direction, x2 function of alpha and beta, E2 hat unit vector of second direction, x3, E3. So, we write a position vector like this. If this point moves to this, let us say M1 dash. So, change in curvature ds, basically curve length, we are interested to know. So, it will be change in r plus dr. We can say that ds square can be written as equivalently dr dot dr. So, first we have to find out the dr. So, r is a function of alpha and beta. So, dr can be find it out. Partial derivative of r with respect to alpha and d alpha plus partial derivative of r with respect to beta d beta, and where r comma 1 can be designated as del r by del alpha and r comma 2 can be designated by del alpha del beta. So, basically comma is representing the differentiation with respect to space coordinates. So, ultimately the dr can be represented in very compact form r comma 1 d alpha plus r comma 2 d alpha. As I have said that ds square can be written as dr dot dr. So, r dr is known. So, multiplying with that, taking dot product gives you equation number 8. Now, again we assign r comma 1 is E and mixed derivative product of that is assigned f and r comma 2 and r comma 2 is assigned as g. If we represent this E d alpha plus 2f d alpha d beta plus g d beta square as in equation 9, this equation 9 is known as first fundamental of surfaces, where E, F, G are nothing but they are basically that distortion parameters or deformation parameters. So, if we say that the curve length along a curve where as a constant b, basically I will just go to the back equation. In this figure you can see that these are the line where beta is going from b1 to b2 to b3 and this line where beta is constant. Over these lines beta is constant, over these lines alpha is constant. So, for that case ds1, the curve length along the constant curve of beta can be written as under root of E d alpha and ds2 can be written as under root of g d beta. Basically we are interested to find out that can we write in terms of ds square, something like that, ds1 square plus ds2 square, the same like in your rectangular coordinate system dx square plus dy square, similarly like that. So, if parametric curves forms an orthogonal net, means they are perpendicular to each other and their tangents are perpendicular r comma 1 and r comma 2, then we can say that this f will vanish, it will go to 0. Then again E times d alpha square plus G times d beta square. So, making this type of form, E is again under root of E is represented by A1 and under root of G is represented by A2. So, we can say A1 square plus A2 square. So, this is the most important and very useful form in the theory of surfaces. So, quantities A1 and A2 are known as Lamé parameters. For defining any cell surface, we must know the Lamé parameters A1 and A2. A1 and A2 are nothing but basically they are distortions parameters, change in that. If we take this is a perfect rectangle, and if we say that, let us say, so this change is denoted by, or it can be taken care by the constants A1 and A2. Now, we are interested to find out the normal to a surface. We have said that over this surface that a particular point, the tangents are defined like that. So, they lies in a one plane, that is known as tangent plane. Now, we are interested to find out a unit normal, like your class 12 level or undergraduate level. If two vectors are working, if there is a normal out of the plane, so you can say that A cross B vector upon magnitude of that vector, that will give you the third vector or the direction thumb rule n hat. Same way here, that r comma 1 and r comma 2 lies in one plane and n hat is perpendicular to that, which is known as surface normal or a unit normal vector, that can be found it out, cross product of two vector and magnitude of their. So, cross product of two vector can be found it out, r comma 1 and r comma 2 magnitude and sin theta in between that. So, r comma 1 is what? It is nothing but it is under root of E, and r comma 2 is nothing but under root of G. So, we can say that under root of E G sin theta, and where is the r1 dot product of r2 can be written as cos theta, and that will be under root of G cos theta, which is nothing but f. As we have said that for an orthogonal curvilinear system, if theta is 0, so this product will vanish. So, we can find out cos theta will be f by Eg, and then sin theta can be found it out like 1 minus cos square theta under the root. So, using those relations, it can be found it out Eg minus f square under the root Eg. So, we can find out the angles between that using this formula. If f is there, if f is not there, then it will be just 1, because for theta 90. Sometimes we use these relations because we are going to develop a theory of surfaces for general curvilinear system, and later on we will specialize that it should be only orthogonal system. But that theory of surfaces, like we consider that there is no orthogonal the curvilinear system. So, we assume that f is there, and so cos theta is represented like f by under root Eg and sin theta is represented like this. So, again using the concept that this can be written as under root Eg sin theta, and again sin theta can be represented like this. So, basically n will be r comma 1 cross r comma 2 upon h, where h is nothing but Eg minus f square. The reason is that the calculating the E, G and f are easy compared to calculating the magnitude of this. So, the parametric curve should be arranged such that n points from the concave side to the convex side of the surface. So, basically if the surface is like this, so it will go outside, if this is inside, then it will go to the inside kind of thing. So, depending upon the surface, basically outer to the surface. Normal of surfaces are defined like this. Now, imagine a curve on a surface omega. The curvature k of this curve can be defined as t hat dash is curvature k, curvature vector, and which can be further represented as k n hat. In the previous lecture, we have derived these relations where t hat is nothing but dr by ds is the unit tangent vector, hence it lies in the tangent plane of the surface, and t dash is dt hat by ds. So, most of the cases we are using a parameter s. S is a variable of the arc length along the curve. So, in this that it is a variable and it is varying along the arc length of the curve. And this k vector can be resolved into two components. We can say that in general sense also, let us say a vector A. It can be resolved in two components along x axis and along y axis if it makes some theta with that. So, we can say that A cos theta and A sin theta. Same way this k curvature vector, because it is on a surface, so curvature vector can be resolved into two components, kn and kt, where kn is the normal curvature vector and kt is the tangential curvature vector. So, I will say that it is the curvature of the curve projected onto the plane containing the curves tangent t and surface normal n. So, basically kn lies on the plane where tangent vector and surface normal is there. This plane is normal to the tangent plane to the surface. So, the normal where it is normal lies. So, in that direction curvature kn is defined. Then is the tangential curvature. Sometimes we called it geodesic curvature. It is the curvature of the curve projected on the tangent plane of the surface. So, along that. So, basically kn is outward normal along the normal vector of the surface and kt is along the tangent of the surface. Here the if surface, like you may say that a sphere or a spherical surface, so we can say that a curve on that surface. So, this is our vector k, general vector k, and this is our surface normal n, and this is our tangent plane t. So, that normal curvature vector will lie in the normal plane and kt will lie on the tangent plane. So, kn is along n hat, that is the most important part, and it is proportional to n hat and can be expressed as minus kn n hat. So, if you see that the direction is opposite to n hat, so it will be minus kn. Kn is called normal curvature and unit vector. Already I have discussed the minus sign, then I will say that minus sign takes into account the fact that direction of kn is opposite to the n hat. Normal curvature is a curvature of a normal section of the surface at a point. So, this is very important concept that a normal curvature can be written as minus of kn, this is normal curvature, and n hat unit normal vector. Where minus sign denotes that it is acting in the opposite direction of n hat. Already we have said that it lies in the plane of t hat and n hat. It is lie in the plane of tangent and normal section. So, we can say that n dot dat going to be 0 because they are perpendicular to each other, normal and tangent. If we take the differentiation this equation with respect to s, so first function differentiation, second function as it is, first function as it is, differentiation of second function. This gives a very important relation that differentiation of n hat dash dot t hat can be written as minus of t dash dot n. We are going to use this equation later on. So, first of all, we will say that our basic equation was curvature vector can be divided into two components, normal curvature and tangential curvature. If we multiply with this equation with the normal dot n, then kn dot n plus kt dot n, because kt lies in the tangential plane, so it is going to be 0. So, k dot n hat is nothing but k bar n dot n. So, this is our first equation, and from there we can say that k hat, basically k bar is t hat dash. If you remember that in the previous question I say that it is t hat dash. So, t hat dash dot n is kn dot n. So, substituting there k dot n, so k bar n we have evaluated that minus kn n, so n dot n becomes 1. So, k bar n is just a reverse of it, kn dot n hat, substituting there. Now, kn from here can be written as, it becomes 1. So, kn becomes minus of kn bar dot n dot. We know that k bar n is t hat dash. So, we have written like this. So, we have obtained that t hat dot n hat dot is 0. From there we have obtained that t hat dash dot n is equal to minus of n hat dash into t hat. So, we can use these relations. So, what is n hat dash? Because minus and minus is here, it will get cancelled out. So, ultimately we are saying curvature can be represented at n hat dash dot t. Now, what is n hat dash? N hat is a vector. Okay, like you say that r is a vector and which is a function of alpha and beta. So, n hat dash is dn by ds. T hat is dr by ds. So, we put it together. So, bottom one gives you ds square which is equal to dr dot dr. So, ultimately it is a first fundamental form of equation at the denominator expression for that. The above expression d n hat dot dr, like r is a function of alpha and beta, n hat is also a function of alpha and beta. So, change in normal vector will be n comma 1 into d alpha plus n comma 2 into d beta. Then dr can be written as, already we have know that dr is r comma 1 d alpha and r comma 2 d alpha. If we multiply these two numerator, that gives you this form, that r comma 1 dot n comma 1 d alpha square plus r comma 2 n comma 2 d beta square plus mixed of r comma 1 n comma 2 plus r comma 2 dot n comma 1 d alpha d beta. If we say r comma 1 l comma 1 is l, r comma 2 n comma 2 is n, and this is 2m, then this set of equation 17 is known as second fundamental form of surfaces. So, we have derived that first fundamental form of surfaces, second fundamental form of surfaces. Second fundamental form of surfaces can be used to compute the curvature of the curves obtained by intersecting the surfaces with normal plane or the normal sections of the surfaces. So, the second fundamental form, if we ask you to that, can we derive it? So, we have to start with the k vector, that it is kn plus kt, and then multiply dot n hat, then it will give dot n, and from there we can prove that k bar n is nothing but it is k bar into dot n, and k bar is nothing but t hat dat dot n, and t hat dot that is nothing but n hat dot t, and then from here n hat dash is nothing but dn by ds, t hat is dr by ds. So, the above one is known as second fundamental form of surfaces, and the denominator is first fundamental of surfaces. So, basically the normal curvature can be represented like this. Now, we want to know the alternate expression. Why we are interested in having alternate expression of L, N and M? The reason behind that L is r comma 1 and n hat comma 1. That you know that n hat expression is complex already, r1 cross r2, and magnitude of that. If you know the position vector in explicit form, then evaluating n hat is a complex, and further derivative of with respect to alpha, that is becoming complex. So, we want to get rid of that. Can we express in terms of normal vector? So, we will say that r comma 1 is perpendicular, r comma 1 is perpendicular to n hat, which is true because r dot 1, which is basically tangent vector, lies in a tangent plane and it is the surface normal, they are perpendicular to each other. So, r comma 1 dot n is 0, and similarly r comma 2 dot n hat is 0. So, if you take that r comma 1 is 0, then you can represent and take derivative with respect to 1. So, r comma 1 1 into n hat plus r comma 1 into n hat comma 1. So, this is the expression of L. So, we can write minus of r comma 1 1 dot n. So, L can be represented minus r comma 1 1 dot n hat. So, which is the more simpler form, because position vector is always simpler. So, the derivative taking in first and 2 is easy, 2 times, but in normal section or a normal vector it is difficult one. You have to first find out the cross product, then magnitude of that and expression, and then after that you will take the derivative of that. Similarly, r comma 2 and n hat, if you differentiate it 2, then it give you first function differentiation, second function as it is, and so on. So, this gives you minus of r comma 2 2 and n hat. Similarly, that r comma 1 and dot n, if you take the derivative with respect to 2, this will give you the expression for m. So, for the expression for m will be minus r comma 1 2 dot n hat. So, up to here I have derived the first fundamental form of surfaces, second fundamental form of surfaces and alternate expression for L, and m, because these are required for driving the curvatures. So, Kn, if I write the form of Kn, dn dot dr, dr dot dr, so above is second fundamental, bottom is first fundamental. Now, E, F, G, all R can be expressed in terms of functions alpha and beta, and they will have a constant value at a point on the surface. So, our aim is to find out that maximum and minimum curvature, because this is the definition of normal curvature and we are interested to find out the maximum and minimum normal curvature, and these are function of alpha and beta. So, first of all we will take out common and make it d alpha by d beta form and put it at lambda. So, you define a parameter lambda which is nothing but d by d lambda. Now, we say that if we take the derivative of this Kn with respect to lambda and equate to 0, so that this equation will give you two roots, and the first root will be corresponding to maximum and second root will be corresponding to minimum. So, we have just divided with respect to d alpha, and from here L 2m lambda and lambda square E 2f lambda G lambda square, and take derivative with respect to lambda, which gives you this equation, and ultimately this form equate to 0. If we solve this quadratic equation, we will get two roots, one corresponding to maximum curvature, second corresponding to minimum one. So, these two roots will give extremum value, already I have explained. So, they will be denoted as K1 and K2, and they are known as principal curvatures, and corresponding curves will be known as principal curves. So, basically there are number of lines on that surface. So, they are all curves. So, the curve corresponding to which principal curvature is known as principal curves, and radii R1 and R2 can be obtained just inversing the curvature. So, the important formula R1 is E by L for a orthogonal system. If we say that our curvilinear parameters are orthogonal to each other, then R1 will be E by L and R2 will be G by N. So, we used to remember or use this set of equations that R1 is E by L and R2 is G by N. So, evaluating E, L, G, N for a surface is easy. So, one can find out what is the maximum radius and what is the minimum radius. So, with this our first fundamental form of surfaces and second fundamental of surfaces ends here. After that, I will explain the various theorems, that theorem of Wingert-Tonne, Rodriguez theorem, Gauss theorem. These are also required for developing the cell theory. Thank you.